My name is Ryan Holger. I'm with HVAC Solutions, which is part of Temperature Equipment Corporation. This week's webinar is on radiant heating and snowmelt systems. We're going to focus on radiant floor heating. You can also do radiant wall heating, ceiling heating, and you could also even in commercial buildings do radiant cooling. We're going to reserve all those for future discussions. But today we're talking about radiant floor heating for comfort applications and snowmelt systems. Obviously, because we're going into the heating season, so those seem appropriate. I am recording this presentation, so you should be able to look at it and view it later or share it with a coworker. I'll give you information on that if you need it. We're going to base this on REHAU products, but this is going to be very fundamental, introductory level, if you will, so it applies to any radiant system that you may be working with. All right. So this is from a recent study talking about the importance of green, and we'll talk about a little bit about how radiant heating can fit into that green profile, if you will. But basically, most consumers, 80-some% of consumers, think that being green, being efficient, being better for the environment is a good thing. However, only about 18 or 20% of those folks are actually willing to pay to make things greener. So that's kind of the target audience of some of these things. Radiant, obviously, it's going to have the benefit of comfort. Maybe not obviously, we'll talk about that. Benefit of comfort, the benefit of energy savings. So we've got two things working in our favor here, and most folks should be interested in one or both of those things. All right, so what makes people uncomfortable in general? Inconsistent temperatures, so equipment cycling on and off. You got hot air blowing on you, then you don't have hot air. Hot air, not hot air. So that's an issue. Room differences, temperatures in differences from one room to the other or from upstairs to downstairs. Different temperatures within a room itself. Sitting too close to the window sometimes is too cold. Drafts. Cold surfaces like cold tile floors in your bathroom. Right? Things being too dry in the wintertime, so not enough humidity in the actual space. Dust issues. And then obviously appearance issues. Noise, and then blocking air vents. And we're going to talk about how radiant heating can address all of these items. Right? So radiant floor heating, there's no fans involved at all. We're using pumping and piping as our distribution systems instead of fans and ductwork. So there is a pump involved, which does have some noise associated with it, but that noise is isolated down in the mechanical room. And unlike a fan system, that noise does not get distributed out to the space. We're going to be able to keep temperatures a lot more even with radiant floors, and we'll talk about how that's actually going to work. And it's basically invisible. There's nothing to see. It's built into the floor. There's no ducts, diffusers, things like that that would be visual to the homeowner or building occupants. All right, so this is this little chart here showing the vertical height in a space versus the physical temperature. So the chart goes from 6 inches off the floor up to about 6 feet, which is the height of most people, approximately. And then on the bottom from left to right, if you guys can hopefully see my mouse, it goes from 60 degrees up to 75 degrees. So ideally, for most of us, if we're in a seated type position, 68 degrees is going to be fairly comfortable for us. If we have a forced air system, most of the heat in the space ends up towards the ceiling. So if you look on this chart here, we're up in the upper 70s when we're up at the 6 to 8 foot range, which is pretty unusable to us because unless you're 7 foot tall, you don't really care how hot it is up there at the ceiling. But then down at the floor, it's the opposite side of the equation. Things are typically in the low 60s down by the floor where your feet are. And then to get right in the middle, right here at whatever that is, 4 or 5 feet, that's perfect, and the thermostat's satisfied at 68, but it's hot at the ceiling and cold at the floor. So if you can believe it, heat rises. I know it's a novel idea, but it's true. Right, so what happens with what's different with radiant systems, and we'll talk about this in pretty good detail, is we're not relying on air temperature or convective forces of air to determine how warm or how cold something's going to be. We're actually going to use radiation. So if you know there's 3 types of ways to heat or cool: conduction, convection, and radiation. A typical forced air system is primarily convection. A radiant system is going to be primarily radiant, obviously. So if you look here, things are a lot more even, if you will. In this particular example, we're in that 68, 69 degree temperature range throughout the entire ceiling height from 8 feet down to 6 inches off the floor. And yes, it's a little bit warmer at the floor than it is on a forced air system. That's going to be a good thing if you're barefooted, obviously. But it's a much straighter line here. We don't have as much stratification from ceiling to floor in a space. We're not paying to heat the ceiling like we are in a forced air system. Alright, so things are going to be more comfortable. It's obviously easier to heat from the low end and let the heat rise up towards the ceiling. Cooler air is typically fresher, has more oxygen in it, it's not as dry, and we're going to be able to use that cooler air on a radiant system. So for folks who have a radiant floor system in their house, you probably already know this, but when you have forced air, you're probably setting your thermostat at 72, 74 degrees, something like that. When you have a hydronic radiant system, you're probably setting your wall thermostat at 66 or 68, and in a lot of cases sometimes down to 64. It seems like all the hydronic guys I talk to, they always have their stat on 64. Not 65, but 64. It seems to be the magic number. So you're going to be able to have a lower air temperature in the space, but get higher comfort due to the radiant effect. Like I said, that cooler air is typically going to make it feel fresher in there. I just give you an example. On the left side, upper left side of this is convection-based heating, which is going to include forced air furnaces and things like that. On the bottom right side here is radiant heating. There's a magic line that goes down the middle here. Up the left is air temperature from 40 to 90 degrees, and on the bottom is radiant temperature from 40 to 90 degrees. The air temperature and the radiant temperature are going to be present in both spaces at all times, whether you got a furnace or whether you got a radiator, but the ratio of the two is going to be a little bit different. So if you look here, to keep a space at, say, 75 degrees in the wintertime, we're looking at this range right here. This pink is the comfort area. We can handle lower air temperatures if the radiant temperatures are warmer, and vice versa, right? So if we're on a radiant system, to be comfortable, you'll notice our air temperature is no longer at the 75 degree range. That's actually going to feel warm if you have a radiant-based system. The radiant system is actually kind of shining on your body, kind of like the sunshine. So we actually need cooler air temperatures to be more comfortable because we have a higher radiant temperature. Those cooler air temperatures translate to energy savings. So if you think about it, if you go outside on a 65 degree day and it's sunny, you feel warm. If you go outside on a 65 degree day and it's cloudy, it feels kind of cool. Exact same temperature outside, but whether we have something radiating on our bodies or not makes a difference in terms of our comfort. So with a radiant heating system in a house or in a commercial building, we can tolerate lower air temperatures and still feel equally comfortable. That translates to energy savings. So have you ever heard the term mean radiant temperature? It's basically the average radiant temperature, and it's kind of a function of the radiant heat loss from our body. Our bodies, in many cases, are the radiators. We're 96 degrees. We're radiating heat out all the time. And if we can have the floor slab radiating heat towards us as well, that makes up for the heat that we're losing. If you have a radiant system in your home or in a commercial building, the surfaces in that space are going to be warmer than with a forced air system. That radiant floor is going to be, quote-unquote, shining on the objects. So it'll be warming up your kitchen chairs. It'll be warming up your tile floor. It'll be warming up your toilet seat. Whatever it's shining on, it's going to be warming that. Okay? So we can tolerate those lower temperatures. Like this example here shows 68 degree radiant temperature and a 72 degree air temperature being fairly equivalent to one another. In reality, most people that have radiant systems even go lower than 68, and they're typically in that 64, 65 degree range. Additionally, the cooler the air is in a space, the higher the relative humidity. And I think people probably know this. If you're involved in cooling systems, you know to get humidity out of the air, to wring it out of the air, we have to have pretty low dew point temperatures on the cooling coil. Those cold temperatures cannot have as much moisture in them, so we bring the moisture out. Well, relative humidity is just a fraction of how much moisture is in the air versus how much can we hold. Cold air can't hold as much, so if we have X pounds of water in the air and we change the temperature of the air, the percentage of relative humidity goes up. So if you have cooler air in the space, it's actually not as dry. So the need for a humidifier is diminished and in most cases eliminated. There's no duct work, so there's nothing involved in that in terms of distributing dust and dust mites around the space, so you don't have that working against you. And then flooring objects is a little bit different. So a carpet system in a forced air home is pretty much a necessity in terms of feet comfort, right? Walking on cold tile or something like that is not very comfortable, so you put rugs in your bathroom floor and on your kitchen floor so your feet don't feel as cold. With a flooring system that's radiant based, it's actually quite the opposite. You want to get rid of as many carpets as possible. A carpet is just an insulator, and in this case we want the warm air or the warmness from the floor to rise up to your feet and not have the carpet blocking it, versus a forced air system or blocking the cold from the floor. So the flooring surfaces will be treated a little bit differently in these types of systems as well. Alright, it's also a little bit easier to zone with radiant-based systems. Obviously there are airside zoning systems, dampering systems that work fairly well on forced air systems with furnaces and condensing units. But with a radiant-based system, things can be zoned even further down because of the sizes involved. To zone things very small on an airside system, I mean, to have your own duct for your bathroom would be like, a 3-inch duct. It'd be very tiny. It wouldn't be realistic. So you typically group zones together on an air system. But on a radiant system, you can choose to zone it even smaller. Now, programmable thermostats are an interesting topic with radiant systems. And for those of you that know me, you know that I've been preaching programmable thermostats for as long as I've been in this business, which is now 13 years. I'm a big programmable thermostat fan, especially when you take it off the hold button. But in the case of high-mass radiant systems, and by high mass I mean radiant tubing in concrete, in cases of those systems, programmable thermostats really don't do you much. In fact, they're not really useful at all. Because by the time that floor cools down, 6 or 8 hours later, you're actually getting ready to heat it back up. Because it takes several hours to heat one of these floors up and several hours to cool it down. And you're normalizing it across the whole time frame. So a setback stat is not really useful. In fact, you can save more energy with a radiant system over a forced air system, even without the programmable thermostat factor. If you're going to have a low-mass radiant system, then a programmable stat may be useful. A low-mass system is like this example here on the bottoms of the slide. We don't have any concrete. We have a wood system with panels on them called REHAU panel, which is this manufacturer REHAU terminology for these metal panels. And those panels are designed to spread the heat out across the floor from the tubing. And there's no concrete involved in this. There's no mass. We're not heating up a large mass. We're just heating those aluminum panels, which are heating the tile floor or whatever kind of flooring we have. So we can warm it up and cool it down faster. So in those cases, a programmable stat would be useful as long as you're going to be setting back, say, at least 6 hours. So you're gone for the day at work or in a commercial building at night, those kind of things. Alright, the radiant system can be the primary heating system in a home or in a commercial facility. You don't need to have secondary heating systems. At a maximum, you're probably looking at about 40 BTUs per hour. That's kind of like the absolute most you'll be able to get out of a floor. Anything more than that, the tubes would be spaced way too close, and you literally wouldn't be able to get enough tubes in the space without increasing the temperature, which would be another discussion, which we'll talk about. Like we said, we can warm floors, we can warm walls, we can warm ceilings. There's lots of ways you can do this kind of stuff. You can have hybrid systems, so you could have a radiant floor system in a basement, and then you could have a hot water coil and an air handler serving the rest of the house. You can do that kind of thing. Obviously, the more radiant floors we have, the better comfort we're going to have overall. Additionally, we're able to handle other loads with these systems with these same boilers. Tying a domestic hot water tank into a radiant system is a very common thing to do. The boiler can, for say 10-15 minutes, stop heating the radiant floor and switch over and warm the water in the domestic hot water tank for you to take showers and laundry and all that stuff. And if you pull away from the radiant floor for 15 minutes or even an hour, no one's going to even notice. The temperature of the floor won't even change one bit. So you don't have to oversize boilers to be able to handle that. The boiler you're putting in for your radiant system is already going to be large enough to handle your domestic hot water load. In some cases, you might be able to do the same thing with snow melting, sizing it for the larger of the two loads, and then you're typically not going to need snow melting and full design day heating at the same time. Obviously, design day around here in Chicago is about -4, -5 degrees. Some of you use -10. In any of those cases, that's probably not when it's going to be snowing. It doesn't snow very often when it's below 0 degrees. Most of the snow is going to be happening when it's in that 15 to 35 degree type range. So your peak snow usage from the boiler and your peak heating, space heating usage from the boiler are not at the same time. So you get a little bit of redundancy, or diversity, I should say, in there. Where are you going to get the hot water from? There's lots of ways to get the hot water. Traditionally, you used a cast iron boiler, and then you had a, oops, backwards there. You had a cast iron boiler, and you had a mixing valve. So you took your return water and mixed it back in with your 180 degree supply water in order to make sure you delivered cool enough water to the space. You can't have 100 degree water in the floor. You're going to burn someone's feet. It's not comfortable, and it could be actually dangerous. So you need to take that return water and mix it back down. So you take your, whatever it's going to be, let's say 110 degree return water, and you mix it back in with your 160 degree supply water, and you get whatever, 130 delivered out to the system, something like that. Nowadays, a cast iron boiler is kind of becoming a dinosaur, especially in a higher end efficiency-based system. Almost all radiant systems, especially in our market, are now condensing boilers. Condensing boiler is exactly what it sounds. The cooler return water on the system is going to allow the exhaust air to condense, which is going to be able to help us get higher efficiencies. That's how you get up to the 93, 95, 98% efficiencies that some of these boiler manufacturers have with condensing boilers. So with that being said, condensing boiler likes to be under 130 degrees. If it's above 130 degrees, in most cases it's not going to be condensing, and hence not very efficient. You don't buy a condensing boiler and have it make 180 degree water. So the condensing boilers like to be under 130 degrees. Radiant floor water temperatures definitely need to be under 130 degrees. Those two are a pretty good match. And of course, you can make hot water by numerous other sources. Geothermal heat pumps are becoming more popular for the same reason as condensing boilers. They already like to make cooler hot water, that 110, 120, 130 degree hot water. And then, of course, if you got a bunch of kids around the house and you want them to go chop wood in the backyard, then a wood-fired boiler might make sense. Also, solar collectors on the roof. All right. So lower average temperatures reduce heating costs. So because we're maintaining a lower temperature, in this case 68 degrees versus a typical 72, we're able to save on energy. Every 3 degrees we can reduce the boiler water temperature is going to save 1% of our fuel usage, our fuel costs. So instead of a 180 degree hydronic system, if we're able to put in a 120 degree system from the boiler running at 120 degrees, that's a 60 degree reduction, which saves us about 20%. Just by instead of using 180 degree cast iron boilers with traditional radiators, just by switching that to radiant flooring and condensing boilers, we can save about 20% and have equal comfort in space. Like I said, we're always trying to be under 130 degrees on these systems anyway, which is a good idea. And then in terms of versus a forced air-based system, in addition to the comfort benefits, the other big benefits on the fan energy savings. A typical 2,000 square foot house is using about 1.25 kW for the residential blower fan, which is 1,250 watts. A typical residential pump in that application is 60 watts. It's a massive, massive difference in distribution. It's a lot easier to move water than it is to move air. So it costs a lot less energy to distribute the heating. All right, so typical residential applications, basements are an excellent candidate. Basements are known for having cold floors. People like to walk on a warm floor. Basements are a great application, typically concrete floors. You can pour a thin slab over top of an existing slab, or you can put the piping directly in the single slab. Kitchen floors are great. Bathrooms are great. Garages, if you want to be able to melt off all that snow that falls off your car when you pull it in your garage, another good application. Commercially speaking, really good applications include car dealerships and garages. Car dealerships, it's actually kind of a technician comfort and retention thing. These guys that work on these cars are pretty specific and pretty skilled labor, and they will go work at a different car dealership because they have a radiant floor temperature, a radiant floor system. Laying under a car on a cold concrete slab is not very fun. If that slab is warmed up, it's obviously a lot better. There's an example there. What else do we want to say? Retirement homes are great. Older people typically like things warmer to begin with. Additionally, we talk about snowmelt systems. Having a snowmelt system in front of a retirement home for slip reasons is an excellent application. Daycare facilities, the kids are always down and playing on the floor. Hospitals, the less duct distribution, the better, because the less issue you have, less filtration you have to do on the airside systems. And prisons are a fantastic candidate for these types of systems for radiant heating and radiant cooling, because it's pretty tamper-proof. It's pretty hard to get inside the concrete and mess with the tubing versus an airside system. These are just some examples. Fire stations are another great candidate for the same reason as car dealerships. The fire trucks come in, they have snow on them. That snow is going to melt off the fire truck, and then when it lands on the floor, you want to evaporate that snow off and get rid of it, so you don't have to deal with that. It's also better for the guys working in the bay on the trucks. And then when the fire trucks actually go out and leave, if you had unit heaters in there heating the space, those unit heaters, when the doors are open, all that hot air just sucked right on out of there. And then you close the door and you kind of start heating the air from scratch. If you have a radiant-based system and you open up the dock doors, the radiant floor doesn't really change temperature all that quickly. You can open up the doors for 10 minutes and close them, and you really haven't lost any noticeable amount of heat. Alright, so there's some photos of different examples to show you what tubing layouts might look like. Greenhouses are a good example as well, and as well as animal facilities. A lot of these facilities that produce animals for food products need to maintain certain temperatures. It's kind of crazy we think about it when we're keeping chickens and cows more comfortable than we do people in a typical office building. But they've done the science and the math there to realize that chickens produce more eggs and cows produce more milk when certain temperatures in the space. So those systems make sense. Outdoor athletic fields, Soldier Field has a radiant system underneath it, as do most modern outdoor stadiums. Even though Soldier Field sucks and the turf is horrible, it's not because it's not warm underneath there. So you have to have the radiant system under those fields to keep the roots of the grass warm so they can continue to grow in the middle of winter. Alright, we said we weren't going to really talk much about radiant cooling. Just know that it is possible. It's not a good fit for residential applications. It is a good fit for a lot of commercial applications. It's an entirely different topic that I can talk with any of you about if you like. We do several systems that are radiant cooling based. We can certainly have those discussions. There's a lot of rules that apply to those systems that have nothing to do with the heating side. You can use the same tubing to heat and cool a building. So you can have one distribution system with one set of pipes in the concrete and use that for heating and cooling depending on the season. I'm going to look real quick over at the questions and see if people are typing any questions in that I need to answer. Looks like we're good for right now. Alright, so some of the basics on designing these systems. There we go. It's really slow. Alright, so here are the steps. First step, as with all systems, is heat loss of the space. Whether it's a forced air system, a radiator system, or an in-floor heating system. Finding out the heat loss of the building is the first step, always. And then we'll talk about what to do with that heat loss as we go through here. Alright, like I said, there's three ways to transfer heat in a space. Conduction, which is basically touching something. So if you were to touch a hot pipe in a boiler room, filling that heat into your hand, that would be conduction. Convection is basically transferring heat through air motion. It doesn't have to be air, but that's what it is in most cases. So that's convection. And then radiation is think of it kind of as the sun. The sun is physically shining on you, which is causing your body to warm up. In our case here, the floor is going to be physically shining on you, warming up your body. Additionally, that floor is going to be shining on the other objects in there, like the tile, the bathtub, the toilet seat, the kitchen counter, whatever it is, and warming those things up, and then those things become re-radiators back to the space. That's another benefit of a radiant-based system. If you're putting a radiant-based system in a warehouse facility, for example, or a loading dock, you're warming up not only that floor, but all the objects in there. That floor is shining on all the materials on the racks themselves, the forklift trucks. All those things become re-radiators. So when you do open that dock door, all your heat doesn't jump out of the space through the air. It stays in those materials as long as possible. When we talk about radiant systems, there is a little bit of convection and conduction going on, but 99% of the discussion here is going to be radiant. 99% of the heat is going to be radiant. Alright, so we have to figure out our total heat loss and then think about that in terms of how much square footage we have available. And it's not going to be the square footage of the entire building or the entire home because some of those spaces are going to be unusable to us. Obviously, putting radiant piping under objects like the refrigerator or under an island, in a kitchen, are going to be pretty useless, so we don't use those spaces. Typically, only about 90% of the floor space is actually usable in terms of the radiant system. So you take the the BTU heat loss from your load calc and divide that over the square footage, and that's going to become how many BTUs per hour per square foot we're going to be working with. Typically, a radiant floor can handle about 2 BTUs per hour. Walls are a little bit less because we don't have any convection working in our favor, and then ceilings are basically no convection working in our favor because heat rises, right? So the ceiling's already warm, heat rises up to the ceiling. We're not delivering that heat down to us. You can still radiate the heat down to people, but you're not getting any convection working in your favor. If you do radiant walls, it's kind of like having an old radiator under your window. The hot air rises off the radiator, and you got a little bit of convection going for air motion, and then the rest is radiant. And then floors is all radiant. Typically, we're going to be looking at maintaining the floor at about 85 degrees. If you get much warmer than that, people will feel it as hot and perceive it as hot. And then if you start getting colder than that, obviously it's cold, which is what you have in a normal house anyway. So 85 is kind of the magic number for what we're going to look for the floor temperature. That doesn't mean our water temperature is 85 degrees. That means our floor temperature is going to be 85. We have to go from the water, through the pipe, into the concrete, and then through the wood floor or tile or carpet or whatever, and then by that point it'll be 85 degrees. So we're going to start out with 110 to 130 degree water and end up at 85 in the actual space. Typically, the 3-foot area near the perimeter walls is treated differently than the center of the space. That's because that's where all of our heat loss is occurring, at the perimeter walls and at the windows. So in those areas, we're going to have the tubes spaced much closer to give us more BTUs for that area. And then in the center of the space, we don't really have much heat loss other than through the roof. So the tubing will be spaced wider than that to give us less BTUs in those areas. And like I said, certain objects like bookcases in an office or an island in a kitchen don't need any tubing under them because you're not going to be able to radiate it anywhere anyway. Okay, so there's those examples. We'll skip over those a little quick. Like I said, the maximum is going to be 40 BTUs per hour per square foot. This just gives you an example here to show you an extreme of what you can do with a radiant-based heating system. This is a 400 square foot sunroom on the backside of a house. 3 walls and a roof are made out of glass. The heat loss for this space is 16,000 BTUs per hour, which is 40 BTUs per hour per square foot. So that's within the range. We can handle that with a radiant system. I suppose if this was a glass gazebo and it was glass on all sides, maybe that needs to be a little bit different. But in most cases, you'd be able to handle something like that. Alright, you also have to think about what you're going to be doing with these things. Are you going to be putting the radiant tubes in concrete? Is it going to be thick concrete? Is it going to be thin concrete? What are you going to put on top of the concrete? Putting carpet on top of it versus putting tile on top of it is a huge difference. Tile is a pretty decent conductor of heat, whereas carpet is basically an insulator. So the type of material you put on top of this system is going to determine the water temperature and tubing spacing as well. There's typically 5 sizes of tubing that we're going to be involved with. Residentially, it's going to be 3 sizes starting at 3/8 of an inch. Like I said, the tighter you put the tubes together, the more BTUs per square foot you're going to get. So that's what we're going to do on perimeter zones. And interior zones, we're going to space them wider apart. Just gives you an idea of tubing sales in the United States nationwide. 1/2-inch tubing is by far the most common system used. 3/8 systems are also available and sometimes used, but 1/2-inch tubing is going to be the most common. And then when you get to the more commercial systems and to snow melt systems, that's typically going to be at the 5/8 of an inch tubing. This just gives you an idea on typical spacing. So typical residential slab on grade, which they call thick pour, which means I'm putting the tubing right inside the slab. I'm typically going to have the tube spaced about 6 to 8 inches apart on the perimeter zones, which is that 3-foot border around things. In the interior zones, it's going to be about 12 inches or a foot apart. I don't want to get too much more than that, even though I probably could for heating reasons. But I don't want there to be hot and cold spots in the floor. So I want to be able to have those tubes close enough that you can't notice it when you're walking on it. And then in bathrooms, we're typically going to have tile-based floors, and people are almost always going to be barefoot. You might want the tubing to be a little bit closer, so you don't have those hot, cold spots that people notice. You'll also notice down here certain systems like the REHAU panel, which we mentioned previously. Those have pretty well-defined values for heat loss as well. And then if you're doing a slab over pour, which means I already have one slab, and now I'm pouring a new radiant slab on top of it, then the rules change a little bit because we don't have as much mass to work with. Maximum circuit lengths, which are how long we can run the tubes out. In theory, we can run the tubes as long as you want. If you want to put in 2,000 feet of tubing, great, you can do that. But you're going to have a big, huge base-mounted pump for your house, which is going to be kind of ridiculous, and the energy bill will be astronomical to pump through that tube. The pressure drop will kill you. So typically, we want to limit the length of the tubing circuits based on what the diameter of the pipe is. So for your typical half-inch piping, we're talking about 300 to 350 feet maximum circuit length. If you start getting beyond that, your pump is going to get ridiculously large. If you're using smaller 3/8 inch pipe, then we can go smaller distances, 250. Using larger pipe, 5/8, then we can go longer distances, 400. So the diameter of the tube is going to kind of dictate how long a circuit can be. And if you needed more length, you would just have 2 circuits for one room. If you had a big, huge, massive pole barn, garage type thing, and you needed it to have a longer length, maybe you'd have 2 or 3 circuits instead of one big circuit. To find the flow rate, it's pretty simple. Take the BTUs per hour, which comes from your load calc. We divide it by 500 times the delta T. The 500 is a constant from a much more complicated formula, but for fresh water, it's 500 times the delta T, which typically is going to be 20 degrees, and we'll talk about that more. So it ends up being the BTUs per hour divided by 10,000. That determines what flow we need for our pumps. So if I need 10,000 BTUs per hour, I need 1 GPM. If I need 20,000 BTUs per hour, I need 2 GPM. Just give you an example here of a corner zone versus a regular perimeter zone. These could be bedrooms or these could be offices, whatever you want to think of them as. The corner room, both of these are 250 square foot rooms, but one of them is a corner room with more exterior walls and more glass, so he might need more flow, or more BTUs, 10,000 BTUs per hour, whereas the more interior zone might need 5,000 BTUs per hour. So that means I end up with 1 GPM for one zone and a half a GPM for another zone. If I have different GPMs for different zones, that means I need to have some way to balance that down. So I'm going to be pumping for 1 GPM. That's what my pump's going to be doing. And the guy that only needs half a GPM, he needs to be throttled back, so that way he's balanced with the rest of the system. And that's where these Pro Balance manifolds come in. This is a manifold that REHAU uses, and some other manufacturers have similar things. But up here is where your supply pipes come in, go out, I should say. And over here is where your return pipes come back from the system. And those each have a adjusting balancing valve on there, so I can throttle those back. So I can set this guy for 1 GPM, I can set this guy for a half a GPM, set these other two for something totally different. I got to be able to balance these systems just like I would on any hydronic system or any other airside system even. And I can always do more circuits, like I said. So in this case here, if I had 6 circuits and I needed 3.8 GPM for 6 circuits, it's 0.63 GPM. If I divide that amongst 10 circuits, then I would need less flow because I have more circuits, more surface area. Typically going to target a 20-degree differential on the radiant system. So if I'm supplying 120-degree water to the floor, I'm going to be returning 100-degree water. If I go less than the 20-degree delta between the supply and return water, I'm typically going to need a lot more flow to get the job done, which is going to be much more pumping energy. If I go higher on the delta T, more than 20, say I go 25 or 30 degrees delta T, that would actually reduce my pumping and reduce my electrical energy on the pump, but from the beginning of the tube entering the room to where the tube leaves would be a much bigger differential, and people would actually be able to notice that differential when they're walking on the floor. This part of the floor would feel like 85 degrees, that part of the floor might feel like 75, and you would physically notice it. So 20 seems to be the magic number, which is nice because most of us are used to 20 degree delta T's for other systems anyway. Alright, so assuming we're going to stick with the 10 degree delta T, if we had less, like I said, 10 degrees, I would actually need basically double the flow. If I went higher, I would need less flow. So flow and delta T are directly related to one another. The next step is figuring out how much pump I need. That's typically called the head loss. You probably heard that before. A 10-foot head basically corresponds to 10 feet of water in a standing column and how much pressure it's pushing down on the bottom of that column. So that's where the term comes from. If you're talking about PSI, 1 PSI is 2.3 feet of head. Most of you guys probably know that. How do we figure out how much feet of head we need? We got to look at all the piping. In this case, I'm showing a table for REHAU PEX tubing, PEX-A tubing. You need to know that as well as the pressure drops of other things in the system to figure it out. So in this case, at that half GPM flow rate I was talking about, if I have 100 degree water, which means I'm supplying 110 degree water and I'm returning 90, so my average is 100, I have a factor of 0.945 times the length of feet of pipe that I have, of 100 feet of pipe I have. You see that up here. This is the head loss for every 100 feet of pipe. So I'm basically losing 1 foot for every 100 feet, basically. So in my case, on one of my circuits, 2.64 feet, I have 2.48 feet of head loss. Alright, so these are my 6 zones, my 6 circuits coming off my manifold. Remember, each one of these, on the bottom, I got my main water coming in here. I have 6 supply pipes coming off there going to each zone. And then I have 6 return pipes coming back to the return pipe. And then this return goes back to the boiler. These are all my different head losses for my different zones. Which way do I size my pump? Do I look at the smallest one? Do I look at the largest one? Do I add all these together? Is there some other magic formula? A lot of folks don't think about it too much, but typically these zones for radiant systems are going to be put in parallel with one another. This zone is in parallel with the second zone, parallel with the third, and parallel with the fourth, and on down the line. If things aren't parallel with each other, we're only concerned about the worst one in terms of sizing the pump. The worst one in this case is 7 feet. So I don't add them all together. I find the worst zone, in this case circuit number 5, and I go with that. So for the purpose of my PEX zoning system, my radiant system, I need 7 feet ahead for my pump. Additionally, I got to think about all the other stuff in the system. So I got to add in the pressure drop of the boiler, in this case 1 foot. I got to add in the pressure drop of the actual manifold itself, which is published data just like the boiler does. The manifold guys publish the data. There's another foot in this example, and then the pipe itself going from the boiler to the manifold. So before I figured out for these zone circuits I needed 7 feet of head, but to get the water there I need another 5 feet ahead. 1 foot through the boiler, 1.5 feet through this pipe, 1 foot through this manifold system, supply and return, and then 1.5 feet back. So 7 feet for my zone circuits, 12 feet for the system as a whole when you look at it. So my pump gets sized for 12 feet ahead and 3.8 GPM. If my system's going to be vertically different, I can add those guys in there. So in this case, instead of 1.5 feet, I needed 2.3 feet for the piping system. The manifolds stay the same. The boiler stays the same. That doesn't care how high or how low it is. And the radiant floor stays the same. It's just the difference on vertically up and down. Right? It's a little bit longer pipe. For these types of closed systems, like all other closed hydronic systems, the elevation is fairly irrelevant in the calculations. In this previous example, we were going up from 1.5 to 2.3. That's because we need to go up 10 feet to the next floor and then do the 20 feet that we previously had, right? So I used to have 20 feet horizontally. Now I'm going to go up a floor and then go 20 feet. So that's where most of that difference is coming from the 1.5 to 2.3, because my pipe is physically longer. The fact that it's higher is pretty irrelevant for a closed system. If you think about this example here with the Ferris wheel, the motor that turns this Ferris wheel just has to physically rotate it and overcome the friction. It doesn't care that over here is a 300-pound guy and over here is a 300-pound guy. He doesn't have to lift each of them. This 300-pound man coming down is physically pushing that 300-pound man up. So same thing with a water system. The water coming down is pushing the other water directly up, and all we care about is overcoming friction. Piping and the wheel are exactly the same in this example. Okay, so we had 38-foot BTU per head loss, 3.8 GPM is what we need at 12 feet ahead. How do we size the pump? Every pump, just like every fan, has a curve associated with it. If I take 4 GPM down on the bottom, and I take 12 feet ahead on the side, that's my design point of where I'm going to be operating. I want to be to the left of that curve and as close to that curve as possible, and preferably kind of towards the middle of the curve, just like with fans, right? So that pump was too big. If I look at this pump here, 4 GPM, 12 feet ahead. This is actually a 3-speed pump, a low, medium, and high speed pump. I'm right at the medium speed, which is great. It's a good selection. I can use this pump, which is a Grundfos UPS 1558, put it on medium speed, and I'm good to go. Plus, it's kind of nice if I did decide that I overestimated, I could probably throttle it back to low speed and run it there if I needed to. This selection would be a bad choice. At 4 GPM and 12 feet ahead, I'm too far away from that curve. My pump would be way too large, which means I'd have to throttle back manually with balancing valves, which would kill my efficiency. Too large. Like all hydronic systems, we've got to have an expansion tank. This expansion tank is sized for the total volume of the system and the temperature change from the coldest temperature to the hottest temperature. As you guys probably know, temperature and pressure are directly related. If you heat something up or cool something down, the pressure is going to change. You've got pressure, temperature, and volume. Those 3 things. If you change any one of them, one of the other 2 must change. Since we can't change the volume because it's a closed system, that means if we want to change the temperature, we have to allow the pressure to also change, right? So that's why we got to have these expansion systems. So as the pressure changes, we basically let the pressure of the water push down on this bladder and push air down. It's easier to compress air than it is to compress water. That's those guys, all right? So you got to know the volume of the system. These are typical volumes of the pipe itself. So our typical half-inch pipe holds 1 gallon for every 100 feet. Then you have to look at the gallon capacity of the boiler and anything else you have on the system and add those all up to figure out how much expansion you're going to be able to work with here. Okay, that was our radiant summary there. All right, click through here. All right, so going to snow melt systems. We'll talk about those just a little bit just to kind of give you an idea. See if there's any questions. Typed in. No, we're good on questions. All right, so snow melt systems. Everything basically works exactly the same as a radiant floor does. The difference is we're doing it outside. But we're still putting tubing in the ground. We still got a boiler. We still got a pump. We still got an expansion tank. We still have so many BTUs per square foot that we need. Just we're going to need a lot more of those BTUs. Right? So the places that this makes sense are walkways, roads, ramps, car washes, things like that. Typically we're dealing with how much snow is going to be falling in a given amount of time, and the temperature conditions and humidity outside are pretty big factors. It's not realistic to design a perfect system that's going to melt all the snow for every possible snow system. So keep that in mind when you're talking to your customers. Some people think that because they have a snow melt system, they're never going to have to use a shovel or a snowblower or a plow again, and that's simply not true. They may not ever have to use it again, or they may not use it very often, but it's still good to have the shovel in the garage. Most snowfall is going to be occurring between 10 degrees outside and 35 degrees outside. When it's really, really cold outside, it typically doesn't snow. So you got that range there, and some of you probably see it nowadays in your car. You get a little snowflake symbol pops up on your car telling you that it's potentially snow conditions while you're driving. When it's above 35 degrees, that little snowflake never shows up. When it's really cold outside, like -5, that little snowflake never shows up. But most cars, I know my car does it this way, I think it's about 18 degrees to, I think, 36 is when my little snow flag comes up. You can get the weather data from ASHRAE or pretty much 20 other sources to figure out what kind of snowfall conditions you might expect and what kind of temperatures you might expect. So you got to look at the kind of system you're going to have, Class 1, 2, or 3. Class 1 is residential, Class 2 is commercial, and Class 3 is institutional. Really going to depend a little bit on some of the rules of thumb, basically, but we'll kind of talk about them as a group here. Everything else seems to be the same as a radiant floor system. We got it. So that's where our load's going to come from, is our snowfall prediction and how cold it's going to be outside. That's where our load's going to be dictated from. and then everything else is going to be the same in terms of how we circuit things, in terms of how we calculate pumps, select pumps on a chart, all that stuff. All right, so typical residential systems might include walkways and driveways, like that. You can do pavers or cement. This is a fantastic application here. When you have underground garages that have ramps going to them, you probably know that if you build up snow and ice in those ramps, it's very dangerous for vehicles going in and out of that ramp. Sometimes they can't even get up or down. The snow melt and ice melt systems not only are going to melt the snow as it's falling, they're also going to continue to melt it until it all evaporates off, so you don't have to worry about where to drain this so much. It's probably good to point out, too, that a snow melt system is not an energy-conserving system. Radiant floors save a lot of energy versus forced air systems in homes and commercial buildings. But a snow melt system is actually the opposite. Same exact technology, you stick it outside, it's not going to be saving you any energy. So the places to really look at this, in my mind anyway, because I'm an energy-conserving type of person, places to look at this are places where it's going to be a safety issue. So I'm probably not going to put snow melt for a roadway. That's probably going to be a fairly ridiculously large boiler. But a sidewalk, especially out in front of a hospital or a nursing home or a school, something like that where someone can slip and fall, that would be a good application. Like I said, parking garage ramps, I would do the ramp, but I wouldn't do the road leading up to the ramp. All right? Like this example here, perfect. Stairways like this on an old church would be another good example. If those stairways crumble, they eventually got to be rebuilt anyway, new concrete poured. It's a perfect time to put radiant tubing in there and deal with it that way. People won't be slipping on those steps, which are pretty steep to begin with. If you're going to be using this for institutions, which would mean things like helicopter pads or ambulance bays, in those cases we're going to size the system more aggressively because we don't even want to have to think about the chance of it not being able to melt everything off. So in that case, we'll be trading a lot of energy for a lot of safety. There's a helicopter pad being poured right there. I got these all listed at 125 BTUs per hour per square foot. Class 1 system, if you recall, was residential. Class 2 is typical commercial. It's basically the same thing. You're melting snow on a driveway or a sidewalk. It's the same difference. Class 3 systems, you're going to 125 BTUs per hour per square foot is going to be the starting point. You may want to be a little bit more aggressive in the sizing if it's a very critical facility like an ambulance bay or something like that. And every town's going to be a little bit different. That's pretty much for Chicago-type climate zone there. You also got to take into account for what happens at the edges, because in the middle of the snow melt system, all the heat's going up. But at the edges of the driveway or sidewalk, some of the heat is going to the side, and you're heating that ground. You're losing the heat that way. 20% is a very conservative rule of thumb. So if I needed 1,000 square feet at 125 BTUs per hour, that's 125,000 BTUs per hour. And multiply that by a factor of 20% to figure out what I'm going to need. And then my boiler, to get 150,000 output, I may have to put 155 or 160 or whatever into it. And there's something called pickup. Pickup is basically going to be how long it takes to heat the slab initially. And there's a factor we'll be looking at to do that as well. In this case, in this example here, we're talking about an additional 15% added on there to be able to pick this thing up a little faster. There's different ways to control that, and we'll talk about that, including an idle mode, which is going to benefit us there. How thick the concrete is going to dictate how many BTUs per square foot we can handle. Typical 6-inch concrete can handle 15 BTUs per square foot. So if I got 1,000 square feet, times 20 degree delta T, times 15 BTUs per square foot, times that 1.15 factor for the edge losses, is 345,000 BTUs. That's my pickup load, just to get the boiler up and going. So if I'm buying that 150,000 BTU boiler and I need 345 to pick up the concrete, it's going to take me a little over 2 hours to heat this concrete up to snow melting temperature. It's a long time. So you have to know it's going to snow in advance. You've got to be a very good weatherman in that scenario. Spacing. We'll skip this one for right now in the interest of time. Spacing. All right. Flow rate works exactly the same as it did on the other systems. The only difference is going to be you're going to have glycol in here, so you don't get to divide it by 500 times the delta T. You need to know what percentage of glycol you have and put it into the actual formula. So just keep that in mind. Glycol is going to be a flow penalty. It's harder to pump glycol than it is to pump water. So think about that. Typically, we're going to be looking at using probably about 50% glycol in our climate zone, certainly no less than 40% glycol. 40% works perfectly fine. If you've got distribution piping going from one building to another or something like that, you're mixing it with the warm water from in the building. But this is going to be mostly water outside all the time, so you're probably going to want to go with 50% glycol for a snow melt system. Whereas those of you guys who do chillers in the winter, you know that 35 or 40% is acceptable, sometimes even 30. But for a snow melt system that's always outside and always operational, you're going to want 50% glycol. Alright, so that just tells you the same calculation we did before with radiant systems. In this case, it's coming to 2.72 GPMs per circuit. Head loss is calculated exactly the same way. The difference is we're looking at the glycol table for 50% instead of looking at the fresh water table. Other than that, we're calculating the head losses the same way. And sizing the pump the same way. In this case, I need, 13.5 GPM and 18 feet of head. This pump is going to be way too small in this case. Look at this one here, 13.5 GPM, and what was it, 18 or 20 feet of head, or 22 feet of head, that's what it was. Right at the operating curve of this 3-speed pump, this would be a good selection. This is a Grundfos UPS 2699 pump, in that example. There's 3 ways to control one of these snow melt systems. You basically could have the system be totally automatic, where it's turning on and off based on temperature sensors and moisture sensors. So if it's cold enough outside and it's wet outside, that's when we turn the snow melt system on. Once again, cold enough will probably be defined as, say, under 38 degrees, and then we have to detect that and moisture to be able to kick the system on. There's a manual enable with an automatic temperature shutoff, so someone physically turns it on when they see the snow starting to fall, and the system shuts itself off when things warm up to a certain temperature, or when someone turns it off. And then there's a total manual system where you turn it on and you turn it off. So some of the differences here. Just give you an example, 1,000 square feet. In terms of 6-inch concrete, I got 75,000 pounds of concrete to warm up. Typically, the average snowfall occurs at 18 degrees outside. It's between 10 and 35 degrees outside. 18 is actually the average of when it occurs. So we'll use that as our example. It typically falls about 10 times a year around here, and it takes about 8 hours per snowfall on average. So it's about 80 hours of operation to melt snow, 75,000 pounds. So our pickup load in this case ends up being 3.4 million BTUs per year, because it was 345,000 each time, times 10 times. And our melting load is 150,000 BTUs, times 8 hours, which is 1.2 million BTUs, times 10 events, which is 12 million BTUs total. So that's what we're going to use to calculate financially which system to operate. We're going to look at natural gas in our market. It doesn't make sense to use electric. It's too expensive per BTU of heating capacity, and most folks have natural gas available around here. So we look at that natural gas with the manual controls, which means someone turns it on, someone turns it off. It takes about $165 a year to operate this 1,000 square foot snow melt system, which is fairly small. If I do an automatic system and I keep the slab idle, which means I keep it warmed up to a reasonable temperature, say 28 or 30 degrees, and then I only have to heat it 10 degrees to melt, I can respond faster. It doesn't take me 2.5 hours to melt the snow. I can melt it a lot faster, but I got to spend some energy to do that. And that energy spend comes out to be $949 versus $165. So it'll cost more to operate, but it'll take a lot less to melt stuff. Manual operation might be okay for a residence, probably it. If it's a commercial building, you probably have to go to an automatic system. And if it's an institutional facility like a hospital, definitely an automatic system. And the last scenario was I don't have an idle mode and I just turn this thing on and let it run all the time at full bore. It's going to be $1,200. So $950 if I have an idle mode, $1,200 if I don't have an idle mode, and $165 if I only kick it on every once in a while manually. REHAU is a pretty huge manufacturer. They are a European company that does have U.S. operations. They have about 15,000 employees, and they pioneered PEX tubing back in 1968, which was a little before I was born. Right, so I told you how long they've been doing PEX tubing. These guys know what they're doing when they design these products. We do have an office here based in Chicago, obviously. There are other systems that REHAU makes that may be useful to you. Like I said, we have the REHAU panel system, so if you're doing an overlay system and you're not pouring new concrete and you want to put this on top of existing concrete, or you want to put it on a second floor that doesn't have concrete on top of wood, you can do that. These panels help distribute the heat evenly. We have what's called REHAU PEX. Excuse me. Everything is REHAU PEX. The tubing was the red tubing inside with the O2 barrier, but we have what's called Insul PEX, which is a REHAU PEX tube wrapped in a foam insulation in a larger roll. And you can have these up to 4-inch interior diameter, or you can have two 2-inch in one single insulated pipe. We use this for heat transfer from one building to another building, from an outdoor chiller to an indoor chiller, outdoor boiler to outdoor chiller to a building, an outdoor boiler to a building, things like that. We have a new product called EcoAir, which some of you may have heard of. If not, we'll be happy to talk to you about it. It kind of works like an ERV, preheating or pre-cooling the outside air, but in this case we use the ground temperature to do it. So where's my mouse? Okay. So we have a little intake cap, which is this guy here. You see him here out in the backyard in this case. He's bringing air in there through this tubing in the ground, which is an antimicrobial tubing, fully sealed. There's nothing from the dirt getting inside there. Goes through the ground, uses the temperature of the ground to heat up or cool that fresh air, and then brings it into the back of the furnace or the ERV or air handler in a commercial building. So there's a lot of different products that REHAU has, just in addition to PEX tubing. This presentation I gave you guys today was a 1-hour version of a 3-day class, basically. So we just touched on some things, but there is a full 3-day class coming up in October. It's October 6th through 8th in Addison, Illinois here. So if you're interested in that, let me know and I'll get you some more info on that. We do a lot of webinars. Every Monday we do a webinar at TEC here. We also have a full hands-on training lab. In fact, we're going to be starting a boiler class in about 5 minutes in this room, so they're shooting me out. And we have a mobile truck that we also use to showcase stuff. This is our schedule for the year. We're on the second half of the schedule now. The next topic is Stirling makeup air units next Monday at noon, just like this one here. If you need info on that, let me know. And with that, I'm going to just check real quick and see if there's any final questions. And I'm going to go ahead and log off here. Looks like we don't have any final questions typed in. If you do have any questions in the future, you can give me a call at 708-670-6383, or you can send me an email at Ryan, RYAN, .Hoger, HOGER, at HVACSolutions with an S.com. It should be up on your screen there. I thank you for your time.